Yeah, we're good. Whenever you're ready. Awesome. Thank you. Cool. Hopefully you're all where you want to be. We're still so serial. Yeah, if this is what's coming up. So before I go through this, if you see something and you think this isn't for me, feel free to go see one of the other talks. I'm not going to be offended. I want you to see a talk you're actually interested in. With that said, we're going to look at .NET deserialization and how we can use it in red team engagements. So we're going to do the background, right, just so we're all starting on the same page, and then we'll talk a little bit about discovery. So I've got some tooling to give you to help you find new vulnerable apps for this stuff. We'll have a look at some of the things we need to consider for weaponization, and then I've got some slides on detection, telemetry, general ramblings about EDR, that kind of stuff that if you use this for a red team op, you probably want to care about. So yeah, this is me. I get nobody cares about these slides, right? But it is important I give you a little bit of context about why I think I have some business telling you about this stuff. So I am James. I'm on the Targeted Ops team at Trusted Tech. I've been doing InfoSec for 8+ years, the last half of that doing red team stuff. And I was a .NET dev for a while before that as well. So yeah, been around for a while. If you asked me to describe myself, I would tell you I am a hacker, a lockpicker, a meme enjoyer, and a PowerPoint hater. That will become apparent as we go through these slides. I hate PowerPoint. I tried my best. I'm sorry if you don't like it. And if you want to chat, see what's going on, follow what I'm up to, ask me questions about this talk, I'm this guy on Twitter. It will never be X. It's always Twitter. But feel free to see what's going on there. So a bit of background. So, in the beginning of time, when Seal and Cat invented programming, not long after, people invented objects. And we're not going to get into, procedural versus OOP. My only contribution to that argument is pick the paradigm that best suits the task that you're trying to achieve. But if you go down the object-oriented programming approach, you will encounter objects, surprisingly. Now, these are the fundamental building blocks of how OOP works. They allow you to do abstraction, inheritance, polymorphism, all that kind of stuff. And you can broadly define them as an encapsulated unit of data and behavior. So you put all your values of your thing into a place, in code logically, and then you put your methods that act on the thing in the same place. The classic example of this is the person object, right? So you have a person that might have a name, a date of birth, maybe a walk method, some other properties that apply to a person. And if you were building something like a university scheduling app, you might have staff and students who would inherit from people, and staff might have salaries and students might have courses assigned to them, stuff like that. So you would inherit from the person class. All those people have names, date of birth, that kind of common it defines a person stuff, and then you put other properties on top. And the diagram at the bottom here, that's even a cool little laser thing, is another example in UML of a train. So trains have some properties, and then you can apply them to journeys and stuff like that. So when I say object, this is broadly speaking what we're going to be talking about. And when we have objects, we probably want to maintain the state of them somehow. So the classic example of this is the config file, right? So you build an app, you maybe want to have some database connection strings, some other properties that you need to let your app run. And when you close the app, you don't want to have to re-enter them every time, so you want to store them somewhere. But because you're doing OOP, you want them in a config object. So you can do config dot give me the database connection string and get that value. So we want to store this stuff, otherwise the users get angry. And there's a few other reasons why we might want to do this. We store object state for distributed systems like PC, saving application state, sending data over the wire. This stuff happens in a bunch of different places. So how do we do that? Well, you can take the object values. We don't care about the code. We can assume the code is in the place where we're going to use it next time, right? But the values, we take those and we convert them to text. Bear with me, there's another slide in a minute. And then we store that text representation someplace else, a database, a text file, you can write it on a billboard if you want, it doesn't really matter. And then when you want your object back, you do the reverse of that process. So you take the values in your text file and you reconstruct an object based off them. And you just invented serialization, so congrats. So the process of taking an object and turning it into text, we call serialization. And when you want to go the other way, we call it deserialization. When we do this, you can use any format you want to represent the data, right? If you want to use Morse code or cat pictures or whatever, you can do that. That's totally fine. But when we see this in use, normally there's three kind of common formats that we'll encounter. So there's XML, JSON, and binary. And when we display binary, humans are terrible at reading binary data, so we display it normally as base64 encoded data. But it's not base64 when it's used, it's just for display. And here's some examples. So Actually, cool pen, right? The top one is JSON. So this is a person with like a name and an age. Like the top one is JSON. The middle one is XML, and the bottom one is like truncated binary encoded as base 64. And if you ever see, like as an aside, this like A, E, A, 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 D, whack, 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 whack sequence, that probably means you're dealing with like encoded data of some sort, probably an object, and you should probably go poke at that because it probably means you've just found a vulnerability. So this is awesome, right? Like we can store object states, we can recreate them, we can put them on disk in places. It turns out this has some fairly like fundamental security flaws. Like if you've done any kind of app testing for client assessments, you're probably aware of where we're going with this. But if not, like there are some like serious issues with this if you do it wrong. So let's do a pop quiz. Here's some code, and here is like a XML serialized object at the bottom. So what do we think is going to happen if we reconstruct this object based on this XML? Well, we have this like conveniently named like intermediate gadget, and it has this like command setter. This is called a setter in .NET. And then when we run the setter, it's going to take this command value and store it so we can use it later, and then it's going to call the public constructor on this exploit class. It's called exploit, right? Like it's fairly obviously going to do something bad, and it's calling into process start, which is the .NET way of running another process from within your code. So when we deserialize this, we'll create one of these, and this will get executed automatically. Like we call this a magic method because it's executed automatically by the runtime when we like reinstantiate the object. The reason for that is interesting. So we could take this object and build it in memory, right, and then just poke the values into like this. So when you come to read them later, you can just read them out the object, and that would be fine, except in situations where your setters are also doing calculations. So if you have a person with a date of birth value, and you set that date of birth, and then in code kind of like this, you use that to build, I don't know, you calculate the age, you maybe work out if they're like, if they can have state pension or something like that based on that value going in, and you don't call that method, like when you deserialize the object, your program will crash later on when you try and read values that aren't there anymore. So we call setters automatically because we have to. We also call a couple of other like things, like public constructors are always called when the object is recreated because we need to know what state the object is in. So we would call these magic methods, and the whole like chain of this calls into this we would refer to as a gadget chain. So that's the kind of the basic building blocks of .NET deserialization exploits. And when we talk about .NET deserialization, there is one tool that if you look at this in any kind of way, you will come across. That's whysoserial.net. This is the tool for .NET deserialization attacks. There is a Java version of this called whysoserial. The .NET one is, surprise, surprise, the .NET version of it. And this has like a whole bunch of gadget chains in there, like pre-built for you, ready to go. It supports multiple formatters. So formatters are like binary formatter, XML, JSON.NET. There's a whole bunch of them that can do serialization. Most of them are vulnerable in one state or another. Some of them, like binary formatter, can never be safe if you pass user supplied data to them. Others, like XML and JSON, like you can put config options around them to make them safe, but we'll cover that a little bit more later on. And then here is the output of whysoserial for an XML serializer. We're using the object data provider gadget. Don't really need to care about how exactly that works for the purposes of this talk, but this is what it looks like. So this is basically a gadget chain that takes a string, so calc.exe, and passes it into a process start call. And then when you deserialize this, like you will result in calc.exe loading. These gadget chains in whysoserial are all things that are in the .NET framework itself. So the one we saw on the previous slide, that would be a gadget chain in like custom code. These are all framework level, so they are always in the framework and available for you to use. So let's see a couple of examples of the stuff we can do with whysoserial. So this piece of code is going to come up a lot. It's a little demo app that I made for this talk, just so we can have a nice, like, easy way to do deserialization. We're going to put our like payload in here as like base64 encoded string. We're going to get the bytes from it, and then we're just going to pass it into binary format to deserialize. And remember, there's no safe way of doing this, so this will always result in an exploitable condition. And we build a gadget chain. This time it's with Notepad. We do binary formatter, the object data provider gadget chain like we saw on the previous slide. We stick it in here, we execute it, and this is the process tree. So you can ignore MSS, MVMon, that's the Visual Studio debugger. We have still serial.exe underneath, it's got conhost, fine, it's a console app. But then we have this. We have like cmd.exe called notepad.exe. Now, if you're doing bug bounty or like fit client assessment or like web app assessments and stuff where stealth is not a concern for you, this is fine, right? Like go run whatever commands you want. If we're doing this from like a red team point of view, that process tree is probably going to summon the SOC to your location as quickly as possible. Like EDR is going to hate this, you're going to have a bad time, you'll get kicked out the endpoint, and you've just wasted a bunch of time. So most of the payloads in WISO Serial call into process start. And that's just by virtue of the fact that that's what most of the gadget chains do. Now, we can do something else, assuming we don't want to summon the SOC, right? I'm going to make that assumption for the rest of the talk. We can run arbitrary code in .NET. And the ones you're looking for are down here. They have like from file in the gadget chain name. So you can take arbitrary C# code, like a class file, and run it inside another process. And here's an example of that one. So this is the CS file that we're going to run. This is just a basic HTTP post. The only kind of caveat with these is they have to be libraries in the .NET framework. If you use something off NuGet, it's probably not going to work, right, unless it's in the GAC already. But we're just using system.net, which is like core .NET framework. We're going to do like a post message to a URL, and then we build it with this. So we use this activity surrogate selector from file. We target binary formatter. The command is different. So under the hood, WISO Serial is building this for you. So we give it the CS file and some DLLs that it needs to reference just to make the build happen. And then we put it in our exploit code here. We execute it. We get our post back to BERT, and then this is the process tree. Again, you can ignore this bit. But now there's no child processes, right? So we're executing code inside that process. And this, from a red team point of view, is much better. Now we're doing a bad thing inside, hopefully, a trusted application. So there is one problem with this gadget chain, right? If we go back to this slide, notice this line that I added. There is a patch that Microsoft put in for this activity surrogate selector gadget chain. And you have to disable a type resolution check to make it work. Now, we're going to ignore that for now. We will cover it a little bit later, but for right now, we can just say that there is a problem that we need to address in a little bit later on. So hopefully we'll kind of understand a little bit more about how this works and why we'd be interested in it. So let's talk about how we can find new ones. So we have some things we want to do to discover this, right? We want to find vulnerable .NET binaries that we can have a path from user-supplied data to an unsafe deserialized code. And .NET is usually fairly easy to reverse engineer. You don't see many apps that are obfuscated. So we could just start opening apps in .peek is my decompiler of choice, other ones exist. Start looking through the code. You can export it to a project file and open it in Visual Studio and just start searching for stuff. But that doesn't scale well, right? That's super slow. There are tens of thousands of binaries on a Windows endpoint. How do we know which ones are .NET to start with? You're going to spend your 2-week R&D window and achieve nothing if we take this approach. But we can do this better in code. So there are a few ways of figuring out if a binary is .NET. You can just try and open it in .peek or whatever. We've already kind of discounted that one. You can literally just loop over it and grep for the string .NET framework. Now this does work. It's a bit noddy and it probably has some false positives and false negatives, but it will get you most of the way there. You could attempt to load it in .NET Perfection. Now this is .NET's way of running arbitrary .NET code from inside .NET code. It's kind of the best way I can describe it without going way off piste here. But if it loads, then it's .NET, and if it doesn't, it'll throw an exception, and we can assume it's not .NET. We can look at the PE headers, or we can use Mono, which is a similar thing. This Mono works at the IL level, and again, if you load it and it works, it's .NET. The way I'm doing this is with PE headers, so I'm bringing in this PE reader library from NuGet, and I'm just loading it, resolving the headers. If it works, then it's a .NET binary. So now we can just loop through every binary on the endpoint and see if it's .NET, right? So that gets us some of the way there. But then we want to find deserialized calls. And again, we could just go and do this manually and decompile them one at a time and start poking around in them, but that takes a long time. We can automate that as well. So there are a couple of ways of doing this. You can either automate DNSpy or ILSpy. They have DLLs that you can wrap, and you can just use them in whatever language you want, and then just get the decompiled output and then read through them. Or the way I like to do it is just use Mono. So mono.cecil will parse the IL for you. This code is missing a piece up here somewhere where it's actually loading it using Mono, but we're just passing it in here. We pass in an array of strings that we want to search for, so like binary formatter, : deserialize, and it will go find all the references to it in that code. And then, like, we can find all the binaries on the host that are .NET. We can search them for vulnerable, like, deserialized calls. We wrap it all in a console app and put some threading around it, and you end up with this. So that repo should be public. Feel free to go clone and start, like, finding your own vulnerable applications. I do have a couple of outstanding things to add to this. Right now it does a file or all files. I've got a couple of bits of like pending commits to do like in a folder. It's also looking for exes and DLLs, so that would be a config switch. But it works, the code's there, you can use this to go find like new and unusual ways to do things. But we can't do it all, right? So if we look at this slide, it's going to give you output like this. So it'll tell you that this like program has a deserialized call in this location. We still need to figure out if it's actually vulnerable. So you're probably back to doing it manually, right? I'm sure you can automate this with maybe CodeQL or like a commercial code scanning tool. I'm not paying for a commercial code scanning tool for this. CodeQL is a potential. It's on my list to look at if you get there first. Cool. Let me know how that goes. Basically, you want to look for that function, determine if the code is actually vulnerable. So throw it into LinkPad if you're not sure, and it'll soon tell you. And then you need to find all the entry points to that function. You follow that, and then you find the entry points to that one. And what you're looking for is user-supplied data going through a series of method calls until it lands in a vulnerable deserialized call. And Serial Killer can help you with this. So if you find, let's say, a DLL with an exploitable call to the binary formatter, but you can't find any references to it, it might just be in an exe somewhere, right? So put the reference into Serial Killer, search the whole endpoint, and it will find hopefully a reference for you, and you can build an attack chain that way. So what are we looking for? Well, we're looking for arbitrary code execution. Ideally, we want it in a widely used binary, right? There's no point me finding it in a binary that I wrote on my endpoint, because when I send you a fish, it's not going to work. We get bonus points if it's in Windows by default, even more points if it's code signed. Like going back to Brandon and Michael's talk this morning, code signing is a thing that you should be aware of. You get even more points if it's signed by Microsoft. These guys are pointing out that most of the legit binaries are signed by Microsoft in the Windows environment. It makes sense, right? And there are binaries that fit some or all of these requirements, and you just have to find them. But I do have a couple of examples to share with you. Bear in mind, if there are one or two, there will be more. So let's see them. Add in util. This was published by Blueprint's blog fairly recently. It's a Microsoft signed binary. It is on every instance of Windows 10 and Windows 11. You can go find it on your Windows boxes right now. And it has a way to pass user-supplied data into a binary formatted deserialized call. Now, if you can figure out a way of getting one of these payloads to a user and having them run it on a binary on their endpoint, that'd be kind of cool, right? You stage an implant from arbitrary .NET code, and then it's inside a Microsoft signed binary on the endpoint that you didn't have to send to them. That's awesome. I recommend only reading the blog. It's actually quite interesting how they found it and the things you need to do to exploit it. Exhibit 2, add in process.net, .exe. This was published by Netitude. Again, they have a tool for this down here. This one spawns a .NET remoting listener, which ultimately allows an arbitrary deserialized call. And they are triggering this file VBA, chem, that file. There's a few other options there. We'll cover why they're doing it that way in a few slides' time. But again, this is a Microsoft signed binary. I think it's on Windows 10. I'm not sure about 11, but signed by Microsoft and has a trivial path to arbitrary code execution. And then something a little different. So this was found by Nick Landers back when he was at NetSpy, a JSON.NET unsafe deserialized call in Azure Service Bus. So they have a component that sits in the client land and talks out to Azure Power Platform, and he found a path to code execution in there, which got him code execution in Azure first party land. So that is code owned and run by Microsoft in Azure in Power Platform. Third party code is user supplied code. First party is Microsoft. Go read that blog. It is a really good example of how he found a gadget chain in somebody else's code and the weaponization of it. Again, another Microsoft signed utility that got you into Power Platform. I'm sure you can do all kinds of cool stuff in there. So, we've covered a lot of content, right? We can find these things now. We kind of know what we're going to do with them. Let's talk about weaponization. So, we're back to this activity surrogate selector from file gadget chain. Now, This was discovered by James Forshaw, and it's the gadget chain that allows like arbitrary C# to be executed. And it was patched not long after it was discovered in .NET 4.8. And they patched it by making changes to this system workflow component model, which is one of the DLLs that is part of the chain. And then Nick Landers, again, when he was at NetSpy, found a bypass to this and published it. And that bypass was then used in exploits for CVE 2020-1147, the NSA meeting exchange role, and a bunch of others. I think it's used in Aladdin as well. This line from our POC earlier, this is turning off that check. So there are some problems with these like arbitrary code execution gadget chains, right? Like this patch exists, your endpoint is probably running .NET 4.8. So we need to disable that check before we can run arbitrary code, or we're stuck with process start calls, and that just makes everyone sad. So we can disable the check like using this gadget chain that I think Nick committed this to mysocial.net. But it only disables a check. Because it throws an unhandled exception, it will crash out with any other like gadgets that you try and stack with it. So you can disable a check, and then you have to send another command to make like your exploit work. Unfortunately, this only works for the application lifecycle. So something like Exchange, where Exchange is always running, right? And you send it stuff, and then it doesn't end when you send it something. You send it the bypass. That turns the check off, and then you send it the exploit, and then you can exploit that NSA meeting vulnerability. Something like my proof of concept code, where it does the deserialize, and then like the app just exits, it's going to clean up all the app pools, and this check will be disabled the next time you run it. So this is something that we need to account for when we're building these payloads. So what do we do about it? Well, we can either send the bypass and then the payload, which works like some of the time. This is what Aladdin's doing. It's why it's using a file to kick these off. Like they're starting add-in process, they're waiting for the listener to come up, they're sending it the patch, and then they're sending it the exploit. We could abandon hope and just use process start calls and just be forever sad. We could try other gadgets. There are others that use this from file pattern. There's a XAML one and this old dataset old behavior. These are not reliable. For various reasons, they may not work. They probably won't. If you can find them and they work, great, you can use them. But yeah, there's a good chance they just won't work depending on what application you're targeting. The reasons for that, way outside of what I've got time to talk to you about today, suffice to know for the context of this talk that they have problems with their, like, the applications you can use them in. Or we can do some science, right? And we can go and modify the gadget chains that are already in YSO-serial to call arbitrary assembly instead of process start. And this is possible. I'm not going to give you one because, like, I'm handing out free TTPs. Sorry if you were misled into thinking I was going to give you O-days. But, you can find them. I promise you they exist. And if you don't have an internal fork of YSO-serial, like, go be the hero your company needs and start making some improvements to it, there are loads of things you can do to this without finding new gadget chains that just make it a much nicer thing to work with for building payloads. And we'll talk about some of those as we go on through the talk. But I'm going to really cheat here and just assume that you've solved these problems one way or another, right? Otherwise, that's it, talk over and we can all go home. So, you've solved those problems one way or another. What are we going to do now? Right. We have some options. So we could obviously stage an implant, which for most Red Team ops is probably what we're going to want to do. We probably want to get C2 on that endpoint. There are other things we can do. Like we can use .NET Reflection to execute code inside the vulnerable process that we've got an exploit for. Or maybe we could use that like .NET Profiler research that Spectre dropped last month. Like I've not looked at this, but it looks promising. Like if you can run .NET Profiler from in.NET, that probably has some fairly interesting use cases. I'm going to show you Reflection because, yeah, why not? This allows you to execute methods in another assembly with some caveats. So if you have an app that's using tokens to do a thing and you can exploit it with deserialization, you can probably use those tokens. Or if you find an app that's like, go make me a DA and takes a user string, there's no reason why you can't call that method and just make yourself DA. It's going to need some reverse engineering with the app, right? Like you're going to have to do a lot of reversing. It's going to be very context dependent, but if you can pull it off, then you can probably do some really cool stuff with it. And here's a really noddy example. So in my still-so-serial exe, I've added this. Like, it has no references. It's just a public static string. This is one of the caveats. So if it's public static, you can just call it. from inside the program with no other things needed. If it's private or it's an instance level method, you have to create a new instance of the application in memory to call it. And that's fine, you can do that, but if your app has startup related things, it makes it more complicated. But your mileage may vary, go do science and see how far you get. This is our proof of concept code, so all this is doing is looping through every app in the app domain. It's looking for this method signature, the get secret, and it's just going to print it to console when we execute it. So we compile this with the XOV, so we get selected from file gadget, we run it in our code, it finds MS-Corlib, it finds still serial, and then it drops into the program, and then it prints out our secret token, and then it goes through the rest of the apps in there that we don't care about. Notice this one at the bottom, the random name. We're going to cover that in a minute as well. And there's workflow component model in there as well. We're going to cover that as well. But that is part of the gadget chain. So remember that those are there. That will be important shortly. So we built an exploit. We've got this cool thing that does stuff. How do we trigger it? That's really going to depend on the app and how it's executed and how you pass it data, right? So there are some examples. You can use an LNK to run a binary on the host. You could bring your own land. These are signed binaries. SmartScreen doesn't apply at this point. There's no reason why you can't just ship them in an ISO or an exe and run them with a bat file or something. You'd think EDR cares about that, but surprisingly, it doesn't, not all the time. You could do kind of a watering hole style attack and just leave these things lying around and wait for users to happen on them. If you want to do lateral movement, you could use SMB to drop the payload somewhere on a remote endpoint and then either trigger it with WNI or a persistence chain or however you like to execute processes on the remote host. Some ideas for you. You will probably, if you find one of these, already know how to execute it by the time you finish doing the R&D to find it, but here's some ideas. Right, we are approaching the end. I've rattled through this a little quicker than I expected, so we can slow down a little bit. OPSEC considerations. So, the story so far. We've found a vulnerable binary. We're going to pretend that my still so serial exe is a legit Microsoft signed binary. We've seen examples that they exist. You can find more. Go use Serial Killer to find them. I promise you there are lots more of these to find. We're just going to assume demo one is fine for this. We want to stage an implant. So that's a red team thing to do, right? I kick off an implant. We're going to use Sliver because it's cool and more importantly, it's free. So we've built ourselves a gadget chain that works and we have a workaround for that activity surrogate problem. And we put all this effort into building these cool things, and we really want to avoid our LEO day ending up on VirusTotal the first time we use it. So what do we do? Well, this is the code straight out of the Sliver documentation for staging Sliver in memory. So here's one way of doing it. It's not a way I would suggest you use, but if you want to, you can. All this is doing is reaching out to this .woff URL. This is the Sliver staging URL. And then it's using virtual alloc, copying the shellcode into memory and calling create thread and then doing wait for single object. So not the best way of executing shellcode, but it works. This public constructor is what is called when we deserialize this. So this is just calling into this method which does the stuff. It's a pretty good example. You can use these imports in these in these payloads without any issue. It's all .NET Core Framework functionality. And then we drop it into our modified binary. So this is the built version of it. We've still got this type safe check disabled. I don't have a screenshot of Sliver calling in because it's not relevant, but I promise you it works. That's not the important part of this. You'll just have to trust me. But we got stuff like this. So this is Process Hacker. And this, for those of you who don't know, shows you a load more telemetry about running processes than Windows Task Manager. So ETW in .NET is one of the primary sources of telemetry for .NET applications. Now, there are other sources of information, but pretty sure all EDRs at this point are using ETW to get telemetry on .NET stuff. There's way more available than what I'm showing here. Again, this is just for demo purposes, but this is kind of an example of what you can see. So this blue highlighted one, the random app name, this is our assembly that we are recreating with our .NET deserialization payload. And then we have the workflow component model stuff down here as well. These are IOCs, right? If you don't modify ISO serial, and this is an artifact from the way that Why-So-Serial does its building for you. So if you remember, we pass in a CS file and some references, it does the building for us. It's just using a random name. Like, I'm not sure if it comes from Why-So-Serial or MS Build under the hood, but because you're not specifying one, it just has a random assembly name. So if you're a detection engineer and you can consume this telemetry and you suddenly see processes with like random like application names not backed by memory, not backed by disk, like this is in memory, like it has nothing on disk but like behind it, that probably means somebody's messing around with deserialization in your environment. Similar to these where am I pointing to? Component model down here. This being loaded is also an IOC. We've got another slide on that in a moment. Suffice to say, you can get a lot of information from ETW in .NET. So if we add a basic ETW bypass to our payload, all that telemetry goes away. Now, I'm not suggesting that's something you should do without thinking about it. Again, going back to Michael and Brandon's talk from this morning, this is probably suspicious, right? It's something that is not like a legitimate application. That like the EDR will get a callback from a process being started. It will know it's .NET, and now there's just no telemetry coming for it. That's probably not a good thing. The point of this is to highlight that you have some control over the telemetry that's coming out of your applications, right? And there is stuff there that you need to be aware of. So, how do we detect this? Well, we hinted at like the random application name in the app domain. That is one way. This system workflow component model. This is part of the gadget chain. You can see this module in memory, even with ETW disabled. Like it's just down there somewhere. So a thought exercise for the detection engineers amongst you. How many legitimate binaries do you think load this assembly? And then more importantly, how many of them are in your environment and actively being used? And if you could answer those questions, and you can consume this telemetry in a way that allows you to run queries over it, and then you see an application that you know doesn't legitimately use this library, suddenly load this library, well, that's probably something you want to go and investigate, right? And start asking awkward questions like, who booked the red team and didn't tell me? And there are other things you can do with this, right? Like that. I'm sure, like, I am not a detection engineer, I don't pretend to be one, but I am sure that people better at this than me could look at some of these things and build better detections. This is just one example of how you can use this telemetry. But we can also prevent these attacks. Now, I'm not saying that this is something I would suggest you do without putting a lot of thought into it, but it is possible. So, Why-So-Serial makes extensive use of the Microsoft PowerShell Editor DLL. This is in... Without getting too into the weeds, there is a gadget chain underneath the gadget chains that Why-So-Serial uses under the hood to do a lot of its heavy lifting. And there was, maybe still is, an open issue for this not being in .NET Core, which last time I looked at .NET Core deserialization, you couldn't use Why-So-Serial because this didn't exist. So what happens if we just remove this DLL? Well, I've seen a client do this, and it worked really well. So they had a sandbox environment where they were taking user-supplied code and they were executing it. It's not meant to have user interaction. It's certainly not meant to be running PowerShell, right? So they just removed this DLL and a bunch of others. And it worked really well. Like, your gadget chains just stop working. You can try and drop those DLLs back to disk. Doesn't matter. Like, you're not getting a deserialization callback from that. It's super effective. Unfortunately, this DLL is used by stuff. And I don't want to stand here and say, go delete this DLL on all your endpoints and like you won't have deserialization issues anymore because you'll probably break something. But if this is a concern for you and you want to run user-supplied code in a sandbox, something to consider, right? Like we could potentially have a way to prevent these attacks from happening. We are nearly done. I've gone through this much quicker than I expected, so I do have one more thing though. I kind of lied to you throughout this talk. So this is a screenshot from my dev VM when I was doing most of the demos for this, right? Like, for those of you who don't know what this means, it means I turned off AV on my endpoint. And AV really is the final boss for this stuff. So all that stuff we did with Sliver, flagged, unsurprisingly, right? Sliver's like fairly well signatured at this point. Building a stager for Sliver in .NET, flagged. Again, not unsurprising, it's public, like exploit code. executing StillSo serial.exe with a payload containing that stager. Flagged. Now that's getting interesting. I mean, .NET, for those of you who don't know, has AMSI in it now, and AMSI will see everything that you do in .NET. It's in, I think, from version 4.8 onwards, maybe 4.7, I forget. When you run .NET code, it basically has a way of seeing what is being executed. So yeah, there's more work required before you can take one of these and build a working cyber weapon with it. I'm not going to tell you how, because, well, I was hoping this was going to be in about, another 10 minutes time. But here we are early. So there are a couple of options for you, right? You can bypass AMSI. Again, that may or may not be suspicious, and you'd have static signatures to get around at that point as well. You could use a custom C2 that it just doesn't know what it is. You could do something that isn't suspicious, like using publicly available exploit code. That's never a good thing. An exercise for you guys, if you want to go and use this in your own things, you need to deal with AMSI and AV detections as well. So, there we are. I have one more slide for you if you want some background reading stuff. I appreciate you coming. Feel free to ask questions, shout them out. If publicly asking questions is not your thing, come see me after. I'm cool with that. Or grab me on Twitter. Pending questions. Here's a slide for you if you want the top two are background research on .NET deserialization in general, and then the tool release link if you're interested. Any questions? Feel free. Hello.
Do you have any advice for finding new gadgets beyond what you're willing to share with us?
Yes. Spend a lot of time reading the .NET Framework documentation.
Style.
So if you look at the existing gadgets in WhySo Serial, they're fairly not well documented, but self-documenting in that you can see what they're calling into. Go and read the MSDN docs on what those things actually do, and then from there, with enough time, ChatGPT and luck, you can probably combine ideas from some of them to make a gadget that takes the parts of the ones that are executing code and shoehorns it into the ones that are running process start. So the bit you're looking to replace is the process start call. You should be able to take the best of all of them and just kind of stuff it together with a little bit of MSDN reading. So. Thank you. Yeah, good. All right. Anyone else? Yeah, cool. Oh, thank you. I definitely appreciate you coming, and enjoy the rest of your con.